Hello friends, myself Arpan Mangal. I have secured All India rank of 29 in GATE 2017 in the first attempt, and now I am pursuing my MTech from IISc Bangalore. So in the GATE there are few topics which are recently added like Wi-Fi, IPv6. These are the two topics which are added in GATE 2016 only, and in GATE 2016 we have one question from on Wi-Fi, and in 2017 we didn't have any question from these two topics. So there are very high chances that we get question on these two topics. But the problem is on online there is no precise content on how much we have to do on Wi-Fi for GATE. So I thought to prepare this video. It will be benefited for you. In 1 hour or so, I'll cover all the basics of Wi-Fi, which will be sufficient for you to answer any GATE question. So Wi-Fi is nothing. It is a market name of the standard IEEE 802.11, and this is what we have to prepare for GATE. Fine. So nowadays we are heading toward wireless network. So the idea here, it is just a LAN but without wires. So we don't have headache to connect our device. There are long wires coming on. So if we don't have wires, it becomes handy. We can move around with our laptop while connected to the internet. Fine. LAN without wires. In wireless network, we usually use unlicensed frequency of the ISM band and low power. It is because to provide services in cheap and to provide service to the more people. If we use unlicensed frequency, they are available for free in the ISM band. So it will be cheap to provide Wi-Fi services, and low power because then we will be able to provide services to more number of people. There are various techniques in wireless network: 802.11, Bluetooth, and UWB, and so on. But for the GATE syllabus, this is what we have to prepare: 802.11, and this is just and the market name of 802.11 is Wi-Fi. IEEE 802.11 Wi-Fi is a standard which provides a standard of wireless LAN which cover two layers: physical layer and the data link layer. Fine. So in this standard, we have two kinds of services. One is BSS, basic service set, and second is ESS, extended service set. Okay, so what is BSS? BSS is just a unit or a building block. So we have multiple stations which can communicate with each other without any wires. So this form a basic building block. These peers, these have without wires, they can communicate with each other. Fine. So these stations can be mobile or stationary. So this form a basic building block because all the station, so this station covers the range in this circle. So this station can communicate wirelessly in this set. So this form a basic building block or a BSS. In this we can have an optional centralized station also, which we call as access point. It is optional. If we have an access point, we call this architecture as an infrastructure architecture. and the BSS without access point is called ad hoc architecture. So why do we have access point is, if we have a centralized base station, it became easy for us to communicate. If we have a centralized authority which can communicate with this station, so it make easy to communicate. So if we have access point, we call it as infrastructure architecture, otherwise it is a ad hoc architecture. As it is a wireless network, the range of this device in which they can communicate is very less. So the idea is to connect various BSS so that each station can communicate with a larger number of stations. So what we do is, we have the second type of services which we call as ESS, which is extended services. It is nothing but a connection of various BSS. But we will be able to connect these BSS only if we have an access point in that. Fine. So that's why I was saying that if we have an access point, it makes easier to communicate with a larger number of people. So what we do is, we have multiple BSS, and all of these BSS have an access point. And there are various stations. Now a station can be a part of one or two BSS, that's not a problem. Now, so this circle, this is of one BSS, and these nodes can communicate with each other wirelessly. But what if this node want to communicate with this node? Since this node cannot communicate with this node because it is outside its range, so what we can do is, all these access points are connected to each other with a wired network which we call as distributed system. Now this distributed system can be any wired LAN. 802.1 doesn't specify the wired LAN which we have to use here. It can be Ethernet also, anything which you want to use here. So if this node want to communicate with a station which are in the range of this node, it can communicate with them directly. Otherwise, if this node want to communicate with the other station which is outside its range, then it can communicate via access point. So if this node want to communicate with this node, it will communicate via this route. And if this node want to communicate with the node inside this range, it can communicate directly. Now the advantage of having a wired network here is that this wired LAN can be connected to any server or hub or router or anything. So in this way, this node can have access to the whole of the network. Fine. Okay. So based on the mobility, we have three types of station or node. One is no transition nodes, BSS transition stations, and the ESS transition. So if a station has the capability to move inside this BSS, its BSS only, then we call that station as a no transition station. If a node or a station has capability to move to the other BSS which are a part of the same ESS, then that station will be called as BSS station. BSS transition station means it can move within the BSS which are a part of the single ESS, and if the station has capability to move outside the CSS also, we call it as a ESS transition station. But while station move from one BSS to the other or from one ESS to the other ESS, A22.11 doesn't guarantee that the connection will remain continued during the move. So during the move, the connection can be disconnected, but after the move, you will be again connected. So this standard specifies two layers, physical layer and data link layer. In physical layer, this standard has various specifications. So based on the encryption scheme, encoding scheme, or the multiplexing scheme, we have various versions of A22.11, A22.11a, A22.11b, A22.11g. And data link layer, we have two parts, medium access control layer and the logic link layer control. In the MAC layer, we have two sublayers, DCF, distributed coordination function, and the point coordination function. So A22.11 provide two kinds of services, contention free services and the contention based services. So contention free services are optional. So distributed coordination function basically provide contention based services. So this is compulsory, but if we want to have contention free services, we can have a PCF running on top of DCF. Fine. So we will learn about the DCF first and then we move ahead. Okay. So let's consider a situation. A station enter a network. Now this station can be in the range of various access points. So to which access point this station can associate? So this station can associate itself with this access point as well as this access point. So the process or the technique by which the station associates itself to one of the access point within its reach is called scanning. So whenever a station enter a network, it has to do scanning to associate itself with one of the access point. Or suppose this station is initially associate itself with this access point, and after some time it became unhappy with this access point. So then also it can associate itself with the other access point. So this process is called scanning, by which station associate itself to one of the access point. So what is the steps we have to follow to do scanning is, first this station will send a probe frame. So this station will send a probe frame, and all of the access points which are in the range of this station will get this probe frame. Then all the access points which are in the reach of this station will send a probe response frame. All access point. After getting all the probe response frame, this station will associate itself with one of the AP. So this station will select one of the AP and it will send association request to that access point. Station will send frame to that AP. So let's say this station send probe frame to all these access points, and then all these access points will send probe response frame. After getting all the probe response frame, this station will choose one of the access point he want to associate itself with. So let's say it choose this access point. Then this station will send association request frame to this access point, and this access point will send association response frame to this station, and the connection is built. AP will send association response frame. So this is called scanning. Basically, this is called active scanning. Why active? Because in this, the station approaches the access point first and then access point reply. But there is other kind of scanning which we call as passive scanning. So, time to time, all the access point will send a beacon frame. Beacon frame, it is an advertisement by this access point which tells the its capability to each of these stations. So by that, this access point will send a beacon frame which advertises its capability to these stations, and then if this station want to associate itself with this access point, it can send the associate request frame to this access point. So this type of scanning is called passive scanning. Now we talk about the first sublayer of MAC layer, which is DCF, distributed coordination function. So this is a compulsory service, and this DCF provide contention based service. What do you mean by contention based service? It means multiple station content among each other to get access of the channel. For that it uses CSMA CA, carrier sensing multiple access collision avoidance, not collision detection. Unlike in wired, we use CSMA CD, carrier sensing multiple access collision detection. Actually, collision detection is a better technique because if we can detect the collision, we can do retransmission and other thing. But in the wireless network, we cannot do collision detection, and that's why we have to go with the collision avoidance. There are reasons in that in wireless network, we cannot use collision detection. Okay, so if you remember that in Ethernet, when we use CSMA CD, how do we detect the collision? In that, we have a wired LAN and the station is connected to this. While it is sending the data, it is also listening to the channel. While sending the data, it is also listening to the channel, and if it listens some other frequency, it detects that there is some collision. So in order to detect collision, my station has to be full duplex. That means it is capable of sending and receiving signal at the same time. But since, as I said, that in Wi-Fi we want to provide services to the more customer, and we want to be it to be cheap as possible. So Wi-Fi operates at half duplex. In Wi-Fi, so if we want a station to be full duplex, it will be more costly, and therefore Wi-Fi operates as half duplex. So if a station is sending a data on a channel, it cannot listen at the same time. So it's not possible for a station to detect a collision. Second reason by which we cannot able to detect collision is that in Wi-Fi, as you see, that this node is in the this node range in this BSS. So the range of this station is this circle only. So when we want to detect collision, every station must be aware of other station which is sending the signal. But in Wi-Fi, if A is sending the data and C is sending the data, A is unaware that C is sending the data because the strength of the signal, when C is sending the data, the signal strength is less at A. So when A is sending the data, while it reaches to C, the signal strength is very low to detect collision. So C will not be able to know that A is also sending a data. So this is another reason why we can't do collision detection in Wi-Fi. And the third reason is that there are problems like hidden terminal problem, which we'll discuss later, and due to that also we'll not be able to do collision detection in Wi-Fi. So we have to go for collision avoidance. So in DCF we use CSMA CA, carrier sensing multiple access collision avoidance. So what is the process now? We have a source and we have a receiver or sender or a receiver. So since this as Ethernet, we have carrier sensing multiple access. So when this sender or this source want to send some data to this receiver, it first sends the carrier. If the channel is idle, then it will send the data. So as we have in the Ethernet, in the starting, the carrier sensing multiple access technique is the same. We use back of time with a persistence strategy. So initially, the station will set a back of time to 0, and according to its persistence strategy, it may be one persistent, non-persistent, or anything. According to its persistence strategy, it will sense the channel. If the channel is idle, then this station will wait for some time which we call as DIFS time. DIFS means distributed interframe space. Then after waiting for a DIFS amount of time, it sends a control frame to receiver which we call as RDS, request to send. The sender is asking the permission to receiver whether it can send the data to this receiver or not. After receiving the RDS signal from sender, it will wait for ISFS amount of time which we call as short interframe space, and then it will reply with CTS signal clear to send. That means receiver is saying to the sender that it is ready to receive the data. After getting the CTS signal, the sender again will wait for ISFS amount of time, and then it will send a data. After receiving the data, the receiver will wait for ISFS amount of time and will send an acknowledgement. So let's look at more detail. What we are doing is, first of all, source will sense the carrier, whether the carrier is idle or not, and for that it uses the same backoff algorithm and the persistence strategy. Once it finds that the channel is idle, it waits for DIFS amount of time. So as you see, after getting the channel idle also, we are waiting for small period of time. DIFS here, SIFS here, SIFS. Why we are waiting for this period of time? Because now we have to do collision avoidance. We have to take care that after sensing the channel also, there may be chances for the collision. So we are not straight away sending the data or any signal. We are waiting for some period of time, and after that we are sending this control signal. So you see that for collision avoidance, we are straight away not sending the data packet. First, there is a kind of handshaking between the source and the receiver. It first requests whether the receiver is ready to take the data packet or not. When this kind of handshaking is done, then only the source will send data packet to the receiver. So this is another way how we are doing the collision avoidance. Fine. So now you will be able to understand this diagram more clearly. In the start, the source will run the backup algorithm, and according to its persistence strategy, it will sense whether the channel is idle or not. After sensing the channel is idle, it will wait for DIFS amount of time, which is distributed inter-frame space. After waiting for this period of time, it sends a request to send signal to the receiver, and it start a timer. See, in this, how do we know whether the RTS signal is received by the receiver or not? There could be a collision in between. For that, when it sends an RTS signal to the receiver, it starts a timer. So if the CTS signal is received before timeout, then if the CTS signal is received before timeout, then only we'll process afterward. Otherwise, what we will do, we'll increase if the CTS signal is not received before timeout, we will increase the back of time algorithm, back of time, and we again wait for that back of time, and the process again start. If the CTS signal is received before timeout, it means that the receiver is ready to take the data frame. Then also, after receiving the CTS signal, we are waiting for ISFS amount of time, again for collision avoidance. After waiting for ISFS amount of time, we'll send a data frame, and now again, because of the collision, we start a timer. So if we get an acknowledgement before timeout, then it's a success and the packet is received. If we don't get the acknowledgement before timeout, again we'll increase the back of time, and the process will start again. In the meantime, if we reach, after increasing the back of time, if the limit is reached, we can't do anything and we have to abort the process. So this is the whole picture. While for collision avoidance, we are waiting for short period of time, and we are doing a handshaking between the sender and receiver before sending the data packet. Apart from collision avoidance, waiting for this period of time is important because, as I said, in Wi-Fi stations are half duplex. So it may need to change its state from sending state to the receiving state. So for that, some amount of time is needed. So for that also, we before sending up data packet or before listening, we wait for some period of time, and these timings are important for priority. Suppose there are two stations which sends the channel at the same time. So they both will find the channel idle. So if the packet we can give priority to the station. Fine. So see, this is one sender and this is one receiver. It may be maybe this sender is not sending to this receiver. So this is one sender and this is one receiver. This receiver has to send acknowledgement packet or CTS signal, and this sender has to send RTS or data packet or so. If they both station sends the channel at the same time, they both will find it idle. Then this station, because this station, suppose it want to send RTS signal, it will wait for DIFS amount of time, and since this receiver want to send an acknowledgement or CTS, it will wait for ISFS amount of time. So now, if we want that if these two stations sends the channel at the same time, and we want that this receiver should send the packet first because it is sending an acknowledgement or the clear to send signal, so we want to give priority to the acknowledgement packet. So what we can do, we can make DIFS bigger than SIFS, which is generally the case. So DIFS is bigger than SIFS. So if sender or another receiver is accessing the channel at the same is sensing the channel at the same time, because it will wait for more amount of time, receiver will succeed and it will send the acknowledgement packet first before sender can send the RTS packet. Fine. So these intervals are very important to give the priority to the packets for avoiding the collision and to switch between the receiving state and the sending state. For collision avoidance, we also want, when this station is sending some data to this station, we want that other station should not send data in between to avoid collision. So when this station is sending some data to this station, how do other station know that they don't have to send any data? So for that also this handshaking helps. When this station send RTS packet to this station, all the station which are in the range of this source will hear this RTS packet, and in this RTS packet we have a field called duration field, in which it is given the time amount for which these two stations want to occupy the channel. So when the other station which are in the range of this source read this RTS signal, they know that this amount of time the channel is going to occupy. So they start a vector called NAV, network allocation vector. So whenever the other station hear RTS or CTS, and in these packets there is a field called duration field, in which the amount of time this transmission is going to take place, the time is there. So when the other station hear this RTS packet, it start its NAV time. This is a timer, or we call it a network allocation vector. So for this period of time, other station, they are not going to even sense the channel. They will sit idle to avoid collision. So we can add one more thing here, that before sensing the channel, the station check its NAV timer. If NAV timer is expired, then only it sends the channel, otherwise it waits for its NAV to get expired. This is also meant for collision avoidance. So in Wi-Fi, we have two problems. One is called hidden terminal problem and the other is called exposed station problem. So what is hidden terminal problem? Let's say there are three stations, B, A and C. The range of B is this circle and the range of C is this circle. Fine. So let's consider a case when B want to send some data to A and C want to send some data to A. B want to transmit some data to A and C also want to transmit some data to A. But B and C are hidden from each other. They don't know about each other. So when B is transmitting some data to A, C don't know that A is receiving some data from B. So they both can start sending data at the same time and there will be a collision. So this is called hidden terminal problem. Because B and C are unaware of each other, they can both send data at the same time, which will lead to collision. Fine. So how does this handshaking signals help in avoiding this problem is, suppose B and C sense the channel at the same time. Fine. And they both will find it idle. So B will first send RTS signal to A and C also send RTS signal to A. Fine. After listening to the RTS signal from both the sides, A decide whichever data he want the packet first, So he will send the, suppose this is called RTS B and this is RTS C. It will send CTS signal to B. So these two stations, since they want to communicate with A, they first send an RTS signal to A, and A will decide that which request it want to accept, and it send an CTS signal for that. But when A send its CTS signal, C is also in the range. Suppose A want to send CTS signal to B, but since C can also listen to the C can also listen to the CTS signal, when A send a CTS signal to B, C can also listen to that signal. So C know that there may be some hidden node which want to communicate with A, so it will stop sending the data. So this hidden terminal problem can be solved by RTS and CTS signals. Okay. So the second problem we have is exposed station problem. This is a reverse of the previous problem. In this problem, station is not able to send data even when channel is idle. So let's consider one example. This is one receiver, this is one sender, this is another sender, this is another receiver. Okay, so let's consider this case. These are 4 stations. The range of this station is from this station to this station. The range of S1 is from this to this. Range from S2 is this, and likewise. Now currently S1 is transmitting data to R1, and now S2 want to transmit some data to R2. But since S2 is in the range of S1, when S1 is sending data to R1, S2 assume that it cannot send the data to R2 because someone in its range is sending some data. But if you see, there is no problem. S2 can send data to R2 because the channel is, there is no interference. S2 can easily send data to R2. It will not interfere with the transition over here. But S2 will not send because it is hearing the transmission by S1, because S2 is in the range of S1. S2 is in the range of S1. So when S1 is transmitting data to R1, S2 is listening to that. So it assumes that it cannot send data to any station. But it's not the case. S2 can easily send data to R2 because there is no interference. So this is called exposed station problem. Because of this transition, this station is exposed to the entire network and it is not able to transmit data to R2. So how to deal with this problem? So the RTS and CTS signal, which I told you about briefly, can solve this problem only partially. So when S1 want to communicate with R1, it first sends an RTS signal to R1. S1 first send an RTS signal to R1, and since S2 is in the range of S1, S2 will also listen to that RTS. Fine. But when R1 reply to S1 with a CTS signal, then S2 will not listen to its CTS because S2 is not in the range of R1. So for this transmission, S2 will receive the RTS signal, but it will not receive the CTS signal. So by this, S2 can detect that this is an exposed station problem, so it can send data to R2. There is no problem, it can send data to R2. So RTS and CTS signal can solve this problem. So with the help of RTS and CTS signal, S2 can detect the exposed station problem. Means that S2 can detect that S1 is communicating with a node which is not interfering the node he want to communicate with. So what it will do? It will send an RTS signal to R2, but if S1 and S2 are not synchronized, if S1 and S2 are not synchronized, what do you mean by synchronized? Means if their data rate are different, or their packet size are different, so if S1 and S2 are not synchronized, then when S2 send an RTS signal to R2 and R2 send a CTS signal to S2, this CTS signal will not be able to listen, S2 will not be able to listen this CTS signal if S1 and S2 are not synchronized, because this CTS signal will be collide, and if their data rate are different and packet size are different, then S2 will not be able to listen this CTS signal, and hence S2 will not be able to communicate with R2. So this problem is called exposed station problem. Means even if the channel is idle, S2 is not able to communicate with R2. Okay, until now we talk about DSF sublayer of MAC layer, which provide contention based services, and it is compulsory to provide. But there are some circumstances in which I want to give priority to some station to get access to the channel. Suppose I am running only DCF protocol. So in that all of these stations are running CSMA-CA protocol. So any of these stations can get access to the channel. But what if this station want to send some time sensitive frames? Means it is important to get channel by this station first. But if I am running only DCF, there is no mean that I can guarantee that this station will get the channel. Any of these stations which are competing with it can get access to the channel. So for this kind of scenario, when I want to give priority to some station to get access of the channel, what we do is centralized base station, which is access point, it runs PCF protocol, which provides contention free services. So this access point will poll among the station to which it want to give contention free services. Means it will poll this station. If access point want that this station should deliver its packet first without any contention, it will poll this station and it will tell other station to keep quiet till that period of time. So they will remain idle, and only in that period only this station will send the frame. So how access point run this algorithm is the same way. So it will first sense the carrier. If the channel is idle, it will wait for PIFS amount of time. What is PIFS? PCF inter frame space. It will wait for that period of time. After that, it will send a beacon frame. In the beacon frame, there is an information that access point want to poll this station to provide contention free services. So when access point send the beacon frame in the whole BSS, the station which is polled, it will be quiet, but the other station will start their NAV vector, NAV timer, which is network allocation vector. What that does mean? Until the NAV vector, NAV timer is there, all these stations will not even sense the channel. They will remain idle. In that way, this polled station will get chance to deliver its frame without any contention. So when these other stations listen to the beacon frame, they will start their NAV vector. After beacon frame, the AP will wait for SIFS amount of time, short interframe space. After that, it will send a poll frame to make ready the polled station to send its frame. After receiving the poll frame by access point, this polled station will wait for SIFS amount of time, short interframe space time, and after that it will send an acknowledgement that it has successfully received the pole frame, and it will send the data without any contention. After receiving the data, so this station will send data to the access point, and which will be delivered to this wired LAN to the whole network. After receiving the packet from this pole station, the AP will wait for SIFS amount of time, and it will send an acknowledgement. After this transmission is over, it has to inform other station that the contention free services it want to provide it's over. So access point will send a contention free frame to all the station, and when these other station will receive the contention free frame from the access point, they will end their NAV vector, and again the contention based services will start. So that's why we use point coordination function. Just I said that we want to give priority to acknowledgement packet more than the data packet. For that, what we did is that SIFS timer is less than DIFS timer. When a station want to send a data packet, it has to wait for DIFS amount of time, and when a station has to send acknowledgement packet, it has to wait for SIFS amount of time. If SIFS amount of time is less than DIFS amount of time, so if it happens that both the station access the channel or sends the channel at the same time, acknowledgement ACK, the station which is sending acknowledgement packet will get the channel first, because SIFS is less than DIFS, and it will send the packet first. So in this way, we are giving priority to the acknowledgement packet more than the data packet. In the same way, what if access point want to start the contention free services, and at the same time this station is also trying to send the packet? So access point and this other station sends the channel at the same time, and they both find channel idle. But after sensing the channel, AP will wait for PIFS amount of time, and these other station will wait for DIFS amount of time. If I want to give priority to the access point so that the contention free services will start earlier, PIFS has to be smaller than DIFS. If in the so if other station and access point, even if they sense the channel at the same time, access point will get access to the channel first, because PIFS is smaller than DIFS. In this way, we choose the timing of these space SIFS, DIFS and PIFS. Okay, so this is all about the two sub-layer of MAC in the Wi-Fi. In Wi-Fi, fragmentation is also allowed. Since the channel is noisy, if my data packets are very long, it is then if it got corrupted, I have to retransmit the whole big packet. So it is better if I send the small packet. So in Wi-Fi, the fragmentation is allowed. So we now talk about the frame format. All these things which we are going to learn now, you need not to mug up. Just get the brief idea, and if the question came on this, you will be able to do. Fine. So in the frame format, these are the particular fields. 2 bytes are given for frame control. Then we have a D, means duration. Then we have address 1, address 2, address 3, sequence control, which is the sequence number, address 4, frame body, and the FCF, which is the checksum. So in the frame control, which is of 2 bytes, there are various subfields. The first field is protocol version. Then we have type. So in Wi-Fi, we have various type of frame. For example, we have management frame. So if you remember, in the starting I told you about that if the station enter in the network, it have to associate itself with the access point. For that, it send the probe frame, associate request frame, probe frame, associate request frame. All these are management frame. Next type of frame which we have are control frame, which are RTS, CTS, acknowledgement frame. All these are control frame. And then we have data frame. So in frame control we have protocol version. Then we have to specify which type of frame is this. Then in the particular type also we have various subtypes. So for example, if the type is control frame, it could be an RTS frame, CTS frame or acknowledgement. So we have to specify its subtype. Then we have these two particular bits, which means to DS and from DS. DS means distributed system. Distributed system is nothing but the wired LAN which we have in our ESS. So these two bits decide what are these 4 addresses going to be there in the body of this frame. Fine. Okay, so I will define them later. So after frame control, we have duration field which is of 2 bytes. So in case of RTS signal, RTS packet or CTS packet, we have to specify the duration of time we want to occupy the channel. So for that we have the duration field. We specify the time interval we want to occupy the channel in this field. Based on these two fields, we have these 4 addresses. Then for synchronization we have sequence number, and for error detection we have checksum. Okay, so these two bits decide what are these 4 addresses going to be there. So if these two bits are 0 0, what do you mean by 0 0? If 2DS bit is 0, means a packet is not going to distributed system. So actually the complete picture is there. So these are the station and this is the ESS. Fine. So it could be the case that this station want to communicate with this station. So when this station want to communicate with this station, it can communicate it directly because it is in the range of its BSS. Fine. So the frame need not to go to the distributed system. So in this case, both these bits going to be 0. It means the packet or the frame is not going to distributed system and is not coming from distributed system. Fine. So based on that, we have these 4 status. So these are the 4 addresses. In address 1, we place the address of the next destination. So in data link layer, the packet go hop by hop. So we in address 1 field, we specify the address of the next destination or the next hop. In address 2, we specify the address of previous hop or the previous destination. In address 3, we provide the final destination address, and in address 4, we have original source address. So in the first case, when the packet is not going to distributed system and not coming from distributed system, means the packet is communicating with the station directly. In this case, what is the address 1? Means the address of next destination. It is the final destination it want to communicate. So in the address 1, we have the destination address. In address 2, we have to write previous destination address, which is the source itself. In address 3, in this case, we mention the BSS ID. So if this station is communicating with this, so it is in this circle BSS. So we have to specify the BSS ID in this case, and there is no need to specify the original source because address 2 is specifying the original source. So in this particular case, address 4 is null. In the second case, we have 2 DS bit 0 and from DS bit 1. Means the packet or the frame is not going to distributed system, but it is coming from distributed system. So this is the case. So this is a distributed system. So the packet is coming from distributed system to this station. So the packet is coming or the frame is coming from access point to this station. So in address 1, we place the destination. In address 2, we will provide the sending API address. Address 3, we provide the source address, and the address 4 is null here. The third case is the packet or the frame is going to distributed system, but it is not coming from distributed system. Means it is this case. The frame is going from station to this access point. Fine. So in address 1, we will place the receiving access point address. In address 2, we will place the source address. In address 3 we will place the destination address, and address host will be null here. And the final case is the packet or the frame is going to distributed system and it is coming from distributed system. So this is basically this case. In the LAN, the packet or the frame is going from one access point to the other access point. So in this case, the address 1 will have the receiving access point address, address 2 will have sending access point address, address 3 will have destination address, and address 4 will have the original source address. So this is what, so these two bits decide what are these 4 addresses we are going to have. And SC will be the sequence number, and body will range from 0 to 2312 byte, and there will be standard CRC32 checksum of the 4 byte. So this is what we have to do about the frame format. Please don't mug up this frame, these fields and all these bytes, etc. You just need to get the feel. There are some types, subtypes, there are to DS bit, from DS bit, and the address are placed accordingly. You need to know that part only. Okay, now we talk about the physical layer. I don't think actually this part is not important for gate perspective. So I will just give the very brief idea to just give you an idea. Okay, so in physical layer, in IEEE 802.1, we have various specifications according to the multiplexing scheme we are using, encoding scheme we are using, and the security standard we are using. We have various specifications of 802.11. So we have 802.11a, in which the bandwidth which we are using is 5.725 gigahertz. We are using orthogonal frequency division multiplexing as a wireless encoding scheme. We are using phase shift key as a modulation scheme. The speed varies is from 6 to 54 megabit per second, and the range is 25 to 75 feet. In 802.11b specification, the bandwidth is 2.4 gigahertz, and the wireless encoding scheme is DSSS. The modulation scheme is phase shift key. The speed range from 5.5 to 11 Mbps, and the range is from 100 to 200 feet. In the 802.11g specification, the bandwidth is 2.4 gigahertz, and the speed is 54 Mbps, and the encoding scheme which we are using is OFDM. The important part here is just that we are using unlicensed band in ISM. So I told why we are using unlicensed band, so that it is available free of cost to provide cheaper services cheaper. So in physical layer, we are using these encoding scheme, FHSS, frequency hopping spread spectrum, and it is used in original WLAN standard 802.11. We have also DSSS, direct sequence spread spectrum, which is used as an encoding scheme in 802.11b. We have OFDM, orthogonal frequency division multiplexing, which is used as an encoding scheme in 802.11g. In the wireless network, security is main concern because we are using unlicensed band, so it is open to all. So your data is not secure, so you have to go for security. It's the main concern here. So in WLAN security standard, we have WEP, which is Wired Equivalent Privacy Protocol, and it is used as a security. Originally, it is used as security protocol in 802.11b, and it uses RC4 as an encryption algorithm. We have Wi-Fi protected access and WPA. It is a temporal key integrity protocol, and encryption. The main idea here is that encryption algorithm changes the key dynamically for each data transmission. So the key will be changing dynamically for each data transmission. This is the idea here, and the encryption algorithm is same RC4. We have the second version of WPA, WPA2, in which we use, instead of RC4 encryption algorithm, we use advanced encryption standard AES, which is stronger than RC4. So this is what about the physical layer. It was just to give you a brief idea. According to me, it's not as important. There are very less chances to get a question from here in GATE. So almost I have covered every basic concept of Wi-Fi which is important for GATE. So I will advise you not to mug up all the ideas, all the frame format, physical layer standard. You need not mug up everything. Just look at this video twice or thrice and you are prepared for GATE. I think you will be able to answer each and every question of GATE from this topic. Thank you.